Hello everybody. Today we're going to continue our theme of developing on the ideas of how we use computer vision within science by going into a very specific subject, that is denoising images with convolutional networks. So before I get too far into this subject, I do want to express a lot of thanks to Xingcheng Liu, my colleague at Argonne, who gave a tutorial on this a few months ago, and I've reused a lot of his material to develop our class for today. So as I mentioned, what we're going to dig into today is how we can use machine learning to learn functions that denoise images. And while this is an important subject within science, there are plenty of different kinds of measurements that our ability to use are inhibited by the noise in them. This is something that I chose to put a full lecture on for the fact that it provides a great example for learning adversarial machine learning techniques and gives some more examples on how one can use unsupervised learning. And really, the subject that we're going to talk about in general are how generative models, especially the so-called generative adversarial networks, can produce some really good models for generating data. So to recap, generative models are those which take noise and use that to produce data that falls under some complex and hard to define distribution. A really great example of this is the website This Person Does Not Exist, where they've trained a model that takes random noise and uses that to generate colors of pixels that, when put together to form an image, form something that looks like the photograph of a human. It's really quite impressive what it can do. There are also, on the far right, molecular generation techniques that we've learned that can take the space of all possible graphs and learn from it those graphs which look like drug-like molecules. And these ideas extend to other fields of physical sciences like the TomoGAN, which can generate these weak lensing maps which show how mass is distributed through the universe. And it can produce images very quickly on what the universe would look like under different conditions. And the technique that we're going to talk about for using these generative models are techniques for helping denoise tomography images. So tomography is a technique you've probably heard about being used in science. It's also a very common medical technique, CAT scans or tomography scans, where how they're produced is I take a sample, I take an x-ray of it to get a view of what its internal structure is, looking at it from one direction. I then rotate it, I get another image, and I repeat this many times until I get many 2D cross-sections, which, with some clever mathematics, I can reconstruct to figure out what the internal structure of that 3D object is. And while tomography is a powerful tool, one of its disadvantages is the speed that or the slow speed with which you acquire enough of those 2D images to make a really good reconstruction. And the cost of time in being able to develop all of these images has a physical cost to it. Getting time on one of these tomography instruments is expensive. Also, there are some samples that the more pictures you take, the more they degrade. Soft materials, and especially organics, tend to melt or evaporate inside of tomography experiments, especially those at high power radiation sources like the Advanced Photon Source or APS at Argonne. Additionally, you may want to capture images very quickly if the process that you're trying to image is dynamic and changes over time. The more it evolves, the harder it is to reconstruct images, and you may want to get many snapshots of the 3D process, or of the process in 3D as it's evolving. And the main issue with tomography, as you might guess, if I take too few of these images, I get a very poor quality reconstruction like the one shown below, where it's got a lot of artifacts and other noise that are just the result of having too few samples of the image in 2 dimensions. So one simple way you might think of to reconstruct these is I can take a function that simply takes my noisy reconstruction, predicts what the outputs of each pixel would be as a function of those inputs, and then I subtract off that reconstructed image from the original one, the one without the noise in it, and I can gradually retrain that generative model through supervised learning. I take the losses from the pixel by pixel differences, and I keep retraining a model until I get the optimal denoise. And this technique works, but it's got a real problem in that the ways that we qualify a good reconstruction are not necessarily every pixel lining up perfectly. And the problem with this is really well shown by an example that I'm borrowing from Xing Chung that shows how I can make small changes to, say, a handwritten digit of a 2 and easily turn it into an 8 just by changing 3 pixels. Now you can imagine I could change many more pixels out in less important part of the images, like I can add a whole bunch of white space around the edges, and that's not going to change the meaning of the image, but it would have a larger pixel by pixel difference, which in that previous example I would interpret as being a worse reconstruction, and I would change my model to not do that. But there are also other things about this image that, are there other ways we can take that sort of general logic of how I can express whether two images are really different or not, and use them to construct a better loss function for training that generative model. And the way that Xing Chung has done this in his tomography denoising technique called TomoGAN is to combine several different types of image difference functions or loss functions. And the first of which is just that absolute difference between the two images, but I can also use what's called a perceptual loss, where I take the difference between some property computed based on those images. You could imagine that this function f here could be a function that tells me what digit it is, and I could build a loss function that tells me if this machine learning or this image is different based on its perceptual meaning. And another kind of boils down those real qualitative questions about whether these images look the same or not, where I can imagine having a loss function that tells me, is this image real or not, that would pick up information like, I can notice that these 3 pixels that were added here have a very sharp gradient with the surrounding pixels, which isn't present in natural images. You can see the original image has this aliasing this anti-aliasing that makes it smoother. So I can detect right away that something about this image is not right, and if I could learn a function that could tell me, well, how bad of a reconstruction or how bad of a denoising is this, I could perhaps create an even better loss function. Now at this point I'm going to freeze talking about denoising and step into a technique that's been developed for building those kind of models that tell me, well, is this really a good reconstruction or not? Those kind of hard to pin down answers. And those are called Generative Adversarial Networks, which you might recall from one of our previous lectures where we talked about different generative approaches or different ways to train generators. And we talked about this GAN, which takes some noise, uses it to produce a piece of data that is then judged by some second network that tells me whether this is a true piece of data or a false one. And so breaking into that in further detail, this network has 2 components that are each learned. The first of which is a generator function, which is my function that maps some data to some desired distribution of data. We're going to call that point y. And then a final point, or a final network called the discriminator, which takes a look at this data y and predicts whether it's true. It actually came from our target distribution, like colors of pixels that make a human, or denoised images, and tells me whether it's the case or not. And this I train using both my generated images and some notions of true training data. And so the way that these two networks are trained is in a two-step process, where the first of which is I train this generator to create better fakes. And the way I do that is starting off with some random data, Z. I then run that through my generative model, G, and my discriminator, D, to calculate what is in effect the probability that I produced a real image given my random data, Z. I can use this to establish a loss function. What I want to do is increase the probability that this function produces real data, or this function G produces real data as qualified by my discriminator, which measures the probability. So if I want to make this whole stack produce more realistic data, what I'll do is I'll adjust the gradients or I'll adjust the adjustable parameters of the generator function such that it increases the probability of producing data that's judged as real. Now the problem with this approach is that I don't yet have a good model for qualifying if data is real or not. So I need to learn that one as well. And that I learned via a second step. So what I do is I make a bunch of fake data by passing different examples of random data through my generator function. I take some examples of real data, and then I measure how right the discriminator was. I include a positive term in my loss term for describing if my discriminator produces a high score for real images being real, and I penalize it for getting high scores for the fake images being real. And this loss function gives me the ability to, say, update the learnable parameters of my discriminator such that discriminator becomes better. And the idea behind deep learning or generative networks is I gradually train these two different networks, the generator, by again adjusting its adjustable parameters, theta, to make it produce data that fools the discriminator into thinking that produced objects are real. And I gradually make the problem more hard by gradually making my discriminator harder to trick. And the idea that over time I'm able to train a network that produces a generator that produces more data that passes my discriminator's test of being real or not. And my discriminator gets gradually better at picking out fakes. And so if you think about I gradually getting a harder test for creating data from my desired distribution, and I'm gradually making that test harder, or my generator can gradually get better at creating kind of fake data that appears to be real. And this is something that has really been a noteworthy development in machine learning, and a lot of people are kind of justifiably scared about it through its use for creating deep fakes. And one that I noticed in the news this morning before I started making the lecture slides for today was showing that someone has created a series of viral videos where they have edited a video to make them look and sound like Tom Cruise, and it's very unsettling. And this is something that has been known for years. I remember a few years ago they showed a doctored video apparently being Vladimir Putin talking about kind of the security or disinformation on the internet. Also, it was created by a generative model by some researchers. And this is really showing how you can take and train a very convincing model that will take data and make something that, even by human standards, looks real. So that aside, we'll go back to talking about TomoGAN. And now you should hopefully know what the GAN in that acronym stands for. So just to recap where we were talking about learning a generative function that takes noisy data and generates a denoised version, and we needed to create something that was better than just taking the pixel by pixel differences. And the way that we're doing that is to keep that message of whether those images match up exactly, but also introduce a perceptual loss, which we'll talk about in another minute, and this generative adversarial term, the so-called adversarial loss, which is that learned function which tells me whether this data appears real or not. So what this looks like in practice is a combination of those three loss functions, where again I trained one based on my adversarial network, where I provided examples of my denoised image, and it tells me if that looks good or not. I also have a perceptual loss, which we'll talk about next, and finally that mean squared error, which is just the pixel-wise difference between the image produced by my generator and that produced by my discriminator, that produced by my actual kind of real images from the reconstruction. So the way that this works for tomography is that my generator function takes in a noisy image and some kind of adjacent slices in 3D and uses that to produce the denoised image using a so-called UNet network. And then I have a discriminator that's just a simple CNN that predicts whether an image is real or whether it's fake. Now that UNet that I mentioned is a convolutional network that has a couple special features to it. So you'll note this is that same figure before, except I'm starting off with my noisy images, and we can walk through how this network functions. I first use a convolutional filter that I'm learning from the data that takes this noise and extracts key features from it. I then pass those features through successive layers of images until I learn some compressed representation that captures the real essence of the data. I then start building that back up. Remember how filters can be not just tools that extract information from an image, but they can also take information about how we know this image was generated and use that to take a simple form and add more information to it. And the way that this UNet functions is it takes information from earlier layers in the network. So here, this is before I've gone through as much compression from the network, and uses those to reconstruct it. So it's effectively like taking an information that contains more information. It's about the original image. It hasn't been compressed as much, and uses that to build back a better representation. And I do this over a series of steps where I'm gradually incorporating data from even earlier in the training process. And that gives me a generative model that can do some pretty incredible things in taking not only the kind of cheap essence of the model distilled through many different successive layers, but can also simultaneously learn information from this larger scale picture, which you can imagine this larger scale picture holds more information of like where are individual features placed, like where are these big circles, and that gives me kind of a better ability to reconstruct this 2D image. The other ingredient that we haven't talked about yet is a perceptual loss. And the perceptual loss is, again, a error function that describes how much different my generated image is than a true image in terms of some features derived from that network. And the way that this is often done in practice is to take some network that was trained for a particular task, like VGG16, which was trained to classify images into different categories, and looking at some of those compressed features about that image that are learned along the course of the way. So I could, for example, take some of the features from later in the network, which captures some of the real in-depth knowledge, or some real kind of core essences about the image, and use the difference between that from our generated image and the true one to express a difference that's, again, kind of describing differences in the essence of the image, not necessarily its pixel values. And combining all three of these losses together with that UNet allowed Xinchun to create a network that is able to remove a lot of noise from networks. Or a noise from tomography images. You can see on the left how a lot of these small-scale features in the image are almost completely occluded by the noise, but with this generative model that's trained to be able to extract the image back, it could be able to infer that, well, these small ribbed parts in similar tomography images that I've seen often have smaller bubbles within them, so it knows that it can place bubbles back in the image even if it did not have a very good picture on exactly where they were from the noisy version. So that should hopefully wrap up our discussion on TomoGAN. Just to recap, this model is trained to give an image, produce a denoised version of it, and it's structured by learning a generator, which is based on the UNet architecture that has these shortcut layers to allow it to reconstruct an image given some both very condensed pictures of what this image is and some less encoded versions of the image that perhaps tell where different features are located in 2D across that image. And the way that one trained this generator was to use 3 different loss functions, the first of which is pixel-wise, where I directly measured differences between the true denoised image and one that was that had some noise in it. I have perceptual loss that measure differences in the features of the image, which are again measured by taking those differences in a feature space of a network that was trained to perform such tasks, because those features have meaning rather than just be kind of plain representations of a pixel value. And then finally it had this adversarial loss, which was from a specially tuned discriminator that would help classify those harder to quantify bits of what makes a tomography image look like a tomography image. And so to wrap up on TomoGAN, we'll talk about one more thing, how it's actually trained in practice. So what you do is you take a high dose image, one that has very little noise in it because we're able to get many different 2D reconstructions. I then throw out a lot of those 2D images to create a simulated low dose version of the deconstruction, and that gives me a lot of training examples of what the tomography looks like, both properly denoised by taking many high resolution images, and what it would look like if I did not have that luxury. The problem with this is I do need a high resolution version to train against, and I can do this in many cases by, say, spending a lot of time to take a very good image for one sample and then reusing that the model trained on that data to reconstruct similar structures from many other from very similar samples. Or I could say find data somebody else has collected that's, say, been published through TomoBank. Or, as we're going to detail next briefly, I can use unsupervised or self-supervised machine learning methods. Those two words are often synonyms for each other. And we can use them to denoise an image without having to acquire a true denoised image, which we need to train that discriminator. So we'll briefly talk about these non-GAN solutions for denoising that solve the problem of what if I don't have true examples of a denoised structure. And these rely on just 2 assumptions for what noise is. So here we view content as something that has predictable variation in space, and that signal doesn't change over time. If I measure the same thing twice, content is not going to move. Noise, on the other hand, is random. It shouldn't have any predictable variation to it, and it changes over time. I don't get the same noise back. So one way you can do this, and this is an example that Xing created based on a paper from 2019 called Noise to Self, where I take my noisy measurement, I hold off, I mask different parts of the image, and then I train a model to kind of guess what those masked portions of the image are. Here I train a loss function that looks only at the portions of the image that were originally masked. That's what this flipped masked, and .x is a element-wise multiplication term. And the idea being, when I'm covering over these images, I should be able to reconstruct it because this content is predictable and it doesn't vary, or it varies randomly between images. But the only thing that should show up in that loss function that I'm actually able to train against is that predictable signal. Another route is a method where I take two different noisy images of the same scene, and I use the fact that my content doesn't change over time, but my noise does, and it should have a mean of 0 over time. So if I take my denoised image produced by my generator, subtract off a measurement with a different noise in it, I should be able to train a model to learn how to minimize that noise that isn't accounted for in my generator. Alright, so that wraps up our lecture for today. We've talked about generative adversarial networks in general that work by training two different models in a two-step process. I first trained a generator model to be able to produce some data, and then I train it such that it fools a tool designed to predict whether that data is fake or not. And then I also trained that discriminator model by giving it both examples of real data, X, and my generated fake samples, Y, and by iterating through this two-step process many times, I can learn both a very good discriminator model at detecting fake data, and I can learn a good generative model for creating good fakes. And one way that this has been used in practice is for TomoGAN, where the generative model took input noisy data and used it to create a denoised image using a UNet based generator model, and by training it to fool a discriminator and also to, say, reconstruct an image exactly with pixel based loss and capture the essence of the image using perceptual based loss, my colleague Xing Chung was able to train a very good denoising model for tomography data.